Have you ever heard that something called the ozone layer is thinning? Or that your aerosol hairspray is what's causing it? Or that it leads to more severe sunburns and UV rays? This is referring to the ozone hole. But what exactly does it all mean? Welcome to Ozone 101. The ozone hole's proper name is actually the Antarctic ozone hole because when it forms over Antarctica. But before we get into what that is, let's first talk about what ozone itself is. Ozone is a gas comprised of 3 oxygen atoms. About 90% of the Earth's ozone exists in the stratosphere, the layer of the atmosphere that extends from 8 to about 30 miles above the Earth's surface. In fact, the stratosphere is often referred to as the ozone layer. Ozone acts as a sunscreen around the Earth, filtering out harmful ultraviolet radiation, or UV rays, which are mainly absorbed in the stratosphere. Without an ozone layer, UV radiation would sterilize the Earth. With a damaged but still present ozone layer, there would be more sunburns, more skin cancer cases, increased cases of eye damage, the wilting and loss of trees and plants, and significantly lessened crop yields. Suffice it to say, ozone is pretty important for the planet. So, what causes the ozone hole? There are several major factors that together lead to the destruction of ozone, thus creating the ozone hole. Those factors are 1. Very strong winds around the South Pole, or the polar vortex. 2. The sun's rays. 3. Chlorine and bromine compounds from ozone-depleting substances. And 4. Cold temperatures below negative 109 degrees Fahrenheit in the stratosphere, which form a specific kind of cloud, polar stratospheric clouds. The polar vortex forms in the southern hemisphere stratosphere during the winter as temperatures drop. And when sunlight returns to Antarctica in late winter and early spring, temperatures are still cold enough to form polar stratospheric clouds, and now there's also sunlight. Chemical reactions take place on the cloud particle surfaces, converting unreactive forms of chlorine and bromine into reactive chemicals. The vortex acts as a sort of container, confining the contents of the Antarctic stratosphere within its bounds, allowing the reactive chlorine and bromine compounds to destroy ozone molecules. That's when depletion can occur on a large scale. With the presence of sunlight, the reactive chlorine and bromine compounds produced during winter begin to deplete ozone molecules by stealing one of their oxygen atoms, leaving just oxygen gas, or O2, in its wake. As long as the polar stratospheric clouds are present, these reactions will occur over and over again, until the ozone is nearly gone. This forms what we call the ozone hole, but that's really a misnomer. It's actually more of a thinned layer. In mid to late spring, the vortex begins to break up, and the polar air depleted of ozone is mixed back into the rest of the southern hemisphere. The ozone hole is gone. Ozone depletion has still occurred, it's just no longer all concentrated in one small area. It's spread around the atmosphere. So why is the ozone hole bigger and longer lasting in certain years? Well, it all comes down to weather. Just like some winters are colder and longer than others on the Earth's surface, the same goes for weather in the stratosphere. If the Antarctic stratosphere stays cold, the polar vortex and the ozone hole within it will persist. And in years with cold springtime temperatures, the polar vortex and the ozone hole are large. Make no mistake, ozone depletion is not a natural thing. It stems from human emissions of chemicals called chlorofluorocarbons, or CFCs. In the early 1900s, refrigerators used toxic gases like ammonia and methyl chloride as refrigerants. Unfortunately, this led to fatalities as the toxic gases leaked out of the appliances. So the search began for a non-toxic and non-flammable chemical that could be used as a refrigerant. Thus, the CFC was born. There are many types of CFCs, but the 2 most common are CFC-11 and CFC-12. In the 1930s, the production and consumption of CFCs began to skyrocket. By the early 1980s, over 300 million pounds of CFC-11 alone were being released into the atmosphere each year. Then, in 1985, British researcher Joe Farman and his colleagues published their research on large seasonal ozone losses over Antarctica. Thanks to the combined efforts of the quick-acting science community, industry, and policymakers, the Montreal Protocol was signed in 1987, restricting the production and consumption of CFCs. Every nation on Earth has now signed the Montreal Protocol. So, for the record, your hairspray and aerosol deodorant hasn't been harming ozone since these laws went into effect in the 80s. But why do we still see an ozone hole today? First, CFCs have lifetimes of 50 to 100 plus years, and it will take some time for the concentration of CFCs in the atmosphere to drastically decline. Second, there are still CFCs being released into the atmosphere today. For example, as an old refrigerator or air conditioning unit deteriorates in a landfill, the CFCs within are slowly released. From the time a CFC is released into the air, it takes about 5 years for its impact to be felt over Antarctica, where depletion will occur. The CFCs emitted at the surface eventually rise into the tropical stratosphere. The ozone in the stratosphere blocks most of the sun's UV radiation, so the CFCs have to rise above most of the ozone layer before sunlight can then break them down. Once they get high enough, solar radiation releases the chlorine, most of which eventually goes into ozone-safe forms like hydrochloric acid and chlorine nitrate. When these compounds make their way to Antarctica, those chemical reactions start up. And if you're wondering why Antarctica, these reactions are unique to the polar regions because of their extreme low temperatures and presence of polar stratospheric clouds. One chlorine atom can destroy thousands of ozone molecules, and millions of tons of CFCs were pumped into the atmosphere from the 1920s through the early 1990s. As CFC concentrations in the atmosphere continue to decline, the ozone hole is expected to gradually become less severe, and scientists expect the Antarctic ozone to recover back to healthy levels around the year 2070.